And welcome to the second video describing the calculations and interpretation of the correlation coefficient, also known as Pearson's R. So this example is going to explore the correlation or the relationship between the number of storks in a geographic region and the number of human births in that area. Because, of course, we all know that storks bring babies. So we want to see if having more storks leads to more babies. That would be the perfect type of study to invoke the correlation coefficient. So what I've got on the screen here is our set of data. We see an X column, which lists our stork population. That is the number of storks that were counted in any given geographic region. So there were 10 storks in this area, there were 12 in that area, and so on. So we were scouring the land for areas that, and counting storks in those regions. If we add all of that up, all total, we saw 241 storks. Now, let's skip a column and look over at our Y column, which is the number of births. This is the number of babies that were born in that same region. So in the region that had 10 storks, we saw 25 babies born. In the region that had 12 storks, we saw 23 babies born, and so on and so on. All total, if we add up our Y column, our sum of Y, we saw that there were 358 babies born. Let me put my sum of X here. Now the remaining columns are those other parts of the formula that we talked about in the previous video. We see a X squared variable, which is just the square. I don't even know how to signify that, but we just squared 10 to get 100, we squared 12 to get 144, we squared 15 to get 225, and so on. So that if we add all of those up, we have the sum of X squared, right there at the bottom, 5,345. In the fourth column, we have the Y squared column, which we just squared 25, we squared 23, we squared 23, and so on. And when we add all of those up, we get 10,916. That would be the sum of Y squared. And then this third column, well, yeah, technically kind of the third, we have, I'll use yellow, we have our XY column. And what that means is we multiply X times Y. So 10 times 25 gave us 250. 12 times 23 gave us 276. 15 times 23 gave us 345, and so on. And when we multiply each XY pair and add them all up, we get 7,449. That is our sum of XY. So we now have all of the parts. Oh, we're missing one part actually. And that is n. N is simply the number of pairs. So we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pairs. So n equals 12. Now we have all of the parts of the correlation formula. You see how easy that was? We just added up all of our x's. We squared each score and add them up, just like what you've done when we calculated the variance and standard deviations of a data set. We added up all of the y's, we squared all of the y's, and summed them up. And that's very similar to standard deviations and variances. We just changed the name of the variable to y because we have 2 from each pair. And then here was something new, is we multiplied x times y and added them up, but that's pretty straightforward, pretty easy. So nothing overly complicated, just squaring and adding a bunch of things. So now that we have the component parts, let's plug them into the formula. All right, so to keep things a little bit neater, I just shortened that whole data table down to our sum. So here we have the sum of x, the sum of x squared, the sum of y, the sum of y squared, and the sum of xy. So let's remind ourselves of that formula. Here's that crazy looking thing. So let's just start plugging in the parts. All right, see if I can fit this all into one screen. So our hour is going to equal, if you remember, our n was 12. So for this part here, we're going to take 12 times, next comes the sum of xy. Sum of xy was 7,449. And then we subtract the sum of x, which was 241, times the sum of y, which was 358. Oops, that's not right. 358. So that takes care of our numerator. We're going to multiply 12 times 7,449. We're going to multiply 241 times 358. And then we're going to do the subtraction there. And in the denominator, this one gets a little bit more crazy, but we take 12 times the sum of x squared, which was 5,345. That's that part and that part. And then we're going to subtract the sum of x, which was 241 squared. Okay, that's part one. And then we multiply. This is an important thing. Don't subtract, but we multiply, doing the same thing with the y variable. We take n, which was 12, times the sum of y squared, which was 10,916. And from that, we subtract the sum of y, quantity squared, which is 358 squared. And then you have to remember this, take square root of that whole thing. So when we reduce that down, we get 3110 divided by 4139.427. There, I fit it in there. So I want you to do the math and see if you get the same numbers that I do within some kind of degree of rounding, but it should be roughly that amount. And so all total, our R comes out to be 0.751. So think about that. Is this R a positive or a negative correlation? Well, hopefully you said positive because there's no negative sign there. Is it weak? Is it medium? Is it strong? Well, 0.75 is actually pretty strong. It's much closer to 1 than it is to 0. So we have a strong positive correlation between the number of storks in the region and the number of live births. So in other words, as the number of storks increases, we tend to see an increase in the number of births, which makes sense because we know the storks are bringing the babies. So what I've put up here now is a scatter plot, if you remember from way back earlier in the semester, a scatter plot of the data. So each spot, each dot on the graph represents one pair. For example, in the stork population, in this stork population, there were 15 storks in the area, which meant there were, I don't have the data right here in front of me, but somewhere around, we'll say 17 or 18 maybe, live births. Here there were also 15 storks in the area, which looks like there were about 33 births. For here we have a couple of areas that had 30 storks each, and there were 33 and 35 live births. So that's what how to read the scatter plot. Each of those dots represents one pair, the intersection of a pair along the x and the y variables. If we look at the general trend here, you see that there is kind of a positive line there, which, if you remember, R of 0.751 is positive. A positive correlation has a slope that is moving up and to the right on a graph, whereas a negative correlation would be moving down and to the right. But we don't have a negative correlation, so let me erase that and clean it up. There we go. So that's sort of the scatter plot fits with our correlation coefficient. Another little point is the steeper the line, that is, the greater the slope of the line. Hopefully you remember slope from, maybe your high school days. The steeper the slope, the stronger the correlation. So a flat line would be an R equals 0. A very perfectly 45-degree angle would be R equals 1.0. And a perfectly 45-degree angled negative correlation would be R equals negative 1.0. So our slope is pretty steep and tends to fit with that R equals 0.751, positive 0.751. All right, now that we know we have a correlation, a positive correlation of 0.751, the next step is to determine if that is significant. Because it could be that we just happen to draw a sample of an area that has a lot of storks and a lot of births just because of normal variation. But the point is this just sampling error, or is it kind of rare to occur naturally by chance alone, and that means that there's a real relationship? Well, to do that, we just look up, just like we've done with t-tests and ANOVA and whatnot, we look up in a table R of our textbook and look for that critical value. So what I've put up on the screen here is just a picture of table R from your textbook. And just a little bit about how to read it. What we're going to need from our data is we need to know our degrees of freedom. Degrees of freedom in correlations is equal to n minus 2. Okay, this is something different because we've always done n minus 1 before. We do n minus 2 for degrees of freedom. So in our instance, we had an n of 12. 12 minus 2 equals 10. So we're going to find 10 degrees of freedom in the table. Then we're going to do, I always default to a two-tailed test because we don't know in advance necessarily if it's going to be a positive or negative correlation. So here is our two-tailed test section. We typically choose an alpha of 0.05. So that's where we're going to enter the table now. We move over from 10 degrees of freedom, move down in that alpha 0.05, and we see that our critical value is 0.576. Just like with t-tests and ANOVA, if our correlation is larger than the critical correlation, then we reject the null hypothesis and we say that this is a significant correlation. Well, 0.751 is in fact greater than 0.576. Therefore, it is significant and we can reject the null hypothesis. There is a real positive correlation between the number of storks in an area and the number of births in that same area. So that's it for calculating a correlation coefficient. Next step now is just work on the interpretation of it. We know we have a correlation of R equals 0.751. We know that that is statistically significant. But now let's see if it's important. If you remember the concept of effect size that we first talked about when we talked about the t-tests, effect size is a measure of the importance of a finding or the meaningfulness in real-world terms. As opposed to just is it statistically rare, which is basically what a significance test is telling us. Well, there are many ways of calculating effect sizes in statistics, but what we are going to do is what's called the coefficient of determination. The coefficient of determination sounds very, very fancy, but you know what? It's probably the easiest statistic you will calculate in this entire class because the formula for it is R squared. That's it. You just square the correlation coefficient. And what this tells us, now this is a little bit tricky, a little bit hard to wrap your brain around, but R squared, or the coefficient of determination, the percent of variability in y that is accounted for or explained by x. Now that's kind of a mouthful too, so let me see if I can draw it out and help you understand it a little bit. So not everybody, actually let me bring in our picture. Okay, I moved things around a little bit to give me some room. Now, variability in y. Let's talk about what that means. So variability in y means not every region had the exact same number of births at the low end of the stork population, or the same number of births at the high end. There was variability. We even saw when there were 20 storks in an area, there were two regions that had 20 storks, one that had 30 live births, and one that had about 35 live births. So there's variability. It's not a perfect correlation. So what the coefficient of determination tells us is what percent of this variability of why there's some low scores and some high scores in the data, what percent of that is explained for once we know what the x variable is. So there's scores that range high and low on the y-axis, and the coefficient of determination tells us, well, given what we know about the stork population, how much of that explains the change in y. If I put it in the form of a Venn diagram, this circle represents all the variability from one region to a next of storks. Okay, some areas have a high amount of storks, high number of storks, some have a low number of storks. This circle represents the number of births in an area. Once again, there's variability in births. Some areas have a high number, some areas have a low number. The overlap is where that R squared, that coefficient of determination, resides. Okay? There are many explanations for why storks congregate in an area. There's many explanations for why there's a large number of births. But once we know the number of storks, we know at least some of the variability, or some reason for the variability in births. So if we were to square R squared equals 0.751 squared, which equals 0.56, that is now just a percent. We know that 56% of the variability in the number of births in an area is accounted for or explained by the number of storks in that area. So that's what the coefficient of determination tells us. It's a little bit easier to understand than just saying, hey, there's a correlation of 0.751 between these two variables, and people will look at you and go, huh? Instead, if you tell them there's a 56% or 56% of the variability in live births is associated with the number of storks in an area, it's a little bit easier to wrap our brain around. So that's what the effect size is in the way that we interpret correlation coefficients. So another way to think about this is in terms of, again, effect size and importance. The more overlap there is in these circles, the more variance that is explained means that a relationship is more meaningful or important. It tells us something more about the world than if there was very little overlap. That is it for effect size. I've got one last little concept statistically to address, and then you'll be experts on correlation. So the last concept that I want to address is the assumptions or what is required in order to be able to calculate a valid correlation. We've got to have data that fit a certain set of parameters. Otherwise, anything that we calculate won't be interpretable or won't be valid. And there are three concepts that you need to know. All right. The first one is that we need a wide range of scores on both our x and our y variables. Wide range of scores. Okay, let me give you an example of that. So the first requirement, I cleaned things up here a little bit if you couldn't tell. The first requirement for calculating a valid correlation coefficient is that you must have a wide range of scores on both the x-axis and the y-axis. If I was interested, for example, in finding a correlation between SAT scores and a person's college GPA, but I was short on time, so I just went to the MIT nuclear physics department and I asked everybody their SAT scores and their GPA, I might end up with a sample of people who probably did pretty well. I tend to think of those people as kind of bright. And so they had very high SAT scores and very high GPAs. Well, the correlation coefficient is actually going to be a little bit odd. It's going to be, almost flat here if we try and draw a line through, the trend of those points. But if we were to have obtained a full range of scores, you see, like on the left, upper left, it's quite a strong positive correlation. So a wide range of scores can change the appearance of a correlation that really exists once we look at the entire population. So that's step one. The second requirement for a valid correlation coefficient, or Pearson's R, is that the data must be linearly related. Now, we talked about this at the very beginning of this series, where we need the relationship to be essentially a straight line. So if we look at these data, just the spots, and we tried to calculate a correlation coefficient with those, we would have developed an understanding of a straight line. Well, a straight line does not best represent those data. Instead, the best representation of those data is a curve. Well, Pearson's R doesn't allow us to take curvilinear relationships into consideration. So we've got to visually inspect our data and make sure that they generally fit a straight line and not a curve of some sort. Okay, that's the second requirement. And there's one more requirement. And that last requirement for a valid correlation coefficient is that we have a homoscedastic distribution. That's quite a mouthful, I get it. Let me just explain what a homoscedastic distribution it is. So a homoscedastic distribution means that the variability in y, that is, the spread between the highest and lowest values of y at one end of the x-axis remains fairly consistent across the whole range of the x-axis. If you look at the slide here, or the picture, there's about a 20-point spread between the highest and the lowest x values across the entire range of x. About a 20-point spread in the y values across the entire range of x. That would be a homoscedastic distribution because it's fairly uniform in its spread. Now let's contrast that with when that assumption is violated. So what just popped up on the right is not a homoscedastic distribution, but a heteroscedastic distribution. There we go. And notice here at the low end of x, we've got very little spread in between the highest and the lowest x values. Y values. But as we move up in x, the spread between the highest and lowest y's gets wider and wider. In other words, the variability in y changes as we change our x. And that is bad. We don't want a heteroscedastic distribution. Luckily, it doesn't happen very often, but we do want to visually inspect it. So this is why Fred's rule of data analysis is always to visually inspect your data, no matter what type it is, no matter what type of test you're doing. You want to make sure that you've got a wide range of scores across both x and y variables. You want to make sure that a straight line best represents the shape of the data. And then lastly, you want to make sure that the variability in the y variable remains fairly consistent across all ranges of the x variable. Visually inspecting your data can do that. And I can guarantee you on the exam you're going to be asked about those assumptions of a correlation coefficient. So make sure you know what they mean and you know how they appear graphically. All right? And that actually brings us to the conclusion of our discussion of correlation. We learned what a correlation was. We learned about the typical statistic R that we use and that crazy formula that we use. It looks crazy, but it's actually fairly simple. We learned how R can range from -1 to +1, that the closer to 0 it is, that means we have a weak correlation. The farther away from 0 it is in either direction, we have a positive or a negative correlation, but it's stronger. And we learned how to determine significance. We learned how to determine the effect size and what the coefficient of determination means. And then lastly, we learned about the assumptions that we need in order to calculate a valid R. So that takes care of pretty much everything. Yeah, I think that's going to bring it to a close. So thanks a lot for paying attention, and I hope this was helpful.